Good morning, students. Today I am going to finish this chapter on phase plane analysis. Okay. As you know that in my last class I had taken one example uh, to explain the method of isocline for drawing the phase plane trajectory on the phase plane. And if you can remember that I took the example of a differential equation for undamped system, which was this, right? X double dot plus x equals to 0. This is a differential equation, and I explained that how to draw the phase plane trajectory using the method of isocline on the phase plane, and the phase plane trajectory is found to be circle. If you take any initial condition on any coordinate, I had shown using graph paper that for any initial point on any coordinate on the phase plane, the trajectory will end at a circle. Okay, and what is the reason for the shape of the trajectory circle? Because it is undamped system. Undamped system, as you know, the time response of the undamped system is oscillatory in nature. But one thing you remember, and the point is to be noted, that this differential equation is linear differential equation. This differential equation is a linear differential equation. Okay, this is x double dot plus x equals 0. uh, Today I will explain that what happens when the differential equation is not linear. Okay, before that I am going to the next topic. Before going to the next topic, I am taking another example to explain the phase plane trajectory for a differential equation. Say this differential equation is E double dot plus 2 zeta omega n E dot plus omega n square E equals to 0. Now this is also a differential equation which is of second order. This is also a differential equation which is of second order. Now you can remember that what is zeta and what is omega n from control system 1. Zeta is called undamped, zeta is called damping ratio, and omega n is called undamped natural frequency. Let us assume the value of zeta is 0.5 and omega n is equals to 1. So if zeta is equals to 0.5, which is less than 1, now what is the case? I think that you can remember that when the zeta is less than 1, what is it called? The system is called as underdamped system. Okay. So the differential equation I am taking for explanation is E double dot plus 2 zeta omega n E dot plus omega n square E, where zeta is a damping ratio which is 0.5 in this case and omega n equals to 1. So the equation now become as E double dot plus 2 zeta into 2 zeta into omega n E dot plus omega n square, as you know, which is 1 in this case, so E equals to 0. So the differential equation is becoming as E double dot plus 2 into 0.5 means only E dot plus E equals to 0. Now this is also a differential equation. Can you tell me that what is this? Is it a linear differential equation or non-linear differential equation? Of course, this is a linear differential equation because you know this is coming from the characteristic equation which is in the form of s square plus 2 zeta omega n s plus omega n square. So where zeta is given, omega n is given, and zeta is taken as 0.5, which is less than 1, which is the case of underdamped system, and these are the cases of linear system. So this is a linear differential equation. Now as you know that what should be my next step, you have to take the assumption for the state variable. Now see, once again this differential equation is again of order of 2, right? So this is also second order differential equation, and you know that the phase plane is constructed by considering x-axis as x1 state variable and y-axis as x2 state variable. Okay, so let us take the assumption. Let E equals to x1, so E dot equals to x1 dot equals to x2, and E double dot equals to x1 double dot equals to x2 dot equals to, now what is E double dot? E double dot means if you keep your E double dot in the left hand side, then on the right hand side of the equation there will be E dot plus E, so minus E dot minus E, so it is nothing but minus E dot minus E, which is minus E dot, what is this? So it is x2, and minus E means x1. So I'm writing the state equation once again. The first state equation is x1 dot is equals to dx1 by dt equals to x2, and the second state equation is x2 dot equals to dx2 by dt equals to minus x2 minus x1. Okay, next step would be, what is the next step? The next step is the slope of the trajectory, and you know that I have to eliminate the time. So if this equation 1, if this is the equation number 2, then the slope of the trajectory is dx2 by dx1 is equals to, if you divide this equation number 2 by equation number 1, it will be minus x2 minus x1 by x2. Now what is dx2 by dx1? Remember, dx2 by dx1 is nothing but the change in y-axis by change in x-axis. So dx2 by dx1 is nothing but the slope of the trajectory. In my last case, I assumed which was m. So m is the slope of the trajectory. Okay. Next step would be finding out the isocline. And what is isocline? As I have discussed in my last class, that isocline will help you to draw the phase plane trajectory. Okay. So, and the equation of isocline is linear if the differential equation is all linear, and the equation of isocline may be non-linear if the equation or differential equation given to you is also, if the differential equation given to you is also non-linear, right? Now what I do, I just keep from this equation, I just keep m equals to minus x2 minus x1 by x2. Now if I cross multiply from this equation, so from equation number 3, mx2 equals to minus x2 minus x1. So take your x2 as common. So mx2, that's why I'm bringing this minus x2 to the left hand side. It will be x2 equals to minus x1. So it will be x2 equals to m plus 1 equals to minus x1. Okay. Now I'm going to find out the slope of the isocline. Okay. And what is the slope of the isocline? Which is x2 by x1. It is not dx2 by dx1. This is x2 by x1, which is a, see, this is also equation of straight line, right? If you keep your x2 here, and it will be minus 1 by m plus 1 x1. Then see, this is as I already said to you that x2 is y-axis and x1 is x-axis, so y equals to minus mx. So this is also again a slope. So this equation is also representing a straight line equation. This is the equation of isocline, right? So the slope of the isocline is x2 by x1 equals to minus 1 by m plus 1, which is slope of isocline. Now, what is the slope if I consider the tangent consideration? Then in my last class, I have taken, say this is the slope of the isocline. So if I consider the tangent consideration, then this slope of the isocline will be tan theta. Now theta is required to draw the isocline, because isocline is a straight line equation. So theta is required to draw the isocline, which is a straight line on the face plane, right? And and since this is the slope of the trajectory, so say this is I'm considering as tan phi. Slope of the trajectory is tan phi, and slope of the isocline is tan theta. Okay. Next task, as I've explained in my last class, is that you have to make a table. Okay. So just first of all you draw the table. Then according to my process, I am just first of all considering the slope of the isocline. So I'm going to consider theta first of all. Theta is nothing but tan inverse of minus 1 by m plus 1. If I assume the theta for drawing the isocline, which is a straight line, and theta is required to draw the straight line, right? Then you can find out the value of m from this equation. So say my second column should be m, and if you find out m, okay, then if you find out m, then from this relation you can find out the angle phi, which is tan inverse m. Okay. Now, as I had explained already in my last class on the graph paper, that uh, instead of assuming m, I am assuming theta at regular interval on the face plane. Okay. So if I consider theta is equals to 0 degree, then the value of AM is found to be infinite, and the value of phi would be 90 degree. And if I take if you take this angle anti-clockwise or anti-clockwise, whatever you prefer, if you consider total 360 degree on the face plane, I'm considering here for the negative angle, so say it is minus 15 degree, and for minus 15 degree the value of M is found to be 2.73, and the angle is 69.89 degree. Similarly, for say I am taking 15 degree apart from the last angle, so that's why my plan is to have the angle such a way that I will start from 0 degree, then minus 15 degree, then minus 30 degree, then minus 45 degree, and so on. Okay, so for minus 30 degree, the value of AM is found to be 0.73, and the angle is found to be 36.24. This is the angle for face plane trajectory. Okay, next, as according to my plan, next angle of the for the isocline is minus 45 degree, and for minus 45 degree the value of M is 0, and the value of phi is 0 degree. For minus 60 degree, the value of M is found to be minus 0.42, and the angle is minus 22.91 degree, and so on. Okay. One advantage of taking the assumption using this process is that if you consider only one coordinate, okay, then the opposite coordinate you can if you can there is no requirement, there is no you don't have to use, actually what I want to mean is that you don't have to use the calculator. Okay, if you calculate for one coordinates at the angle at regular interval for the isocline, okay, then for the opposite coordinate the value of phi would be opposite. Okay, what I want to mean is that, say if it is minus 15 degree, then for the opposite isocline it will be opposite, right? Now I have already drawn the face plane trajectory on my graph paper. I hope you can see the process is same as before, you know. See what is my the first angle for drawing the isocline, 0 degree. So 0 degree isocline is along this axis, and for 0 degree isocline the slope of the trajectory, which is and also for the slope marker angle is 90 degrees, so I am drawing here the slope marker, 90 degree slope marker. Okay, for the next isocline, this is the next isocline. The angle for the next isocline was minus 15 degree, so it is drawn with minus 15 degree. You can put your protector on the origin, and you can take minus 15 degree here. So if you join this line from the origin, it will be a isocline, right, which is a straight line. Now for this isocline, which is minus 15 degree, the slope marker angle is 69.8 degree. So on this isocline, I have drawn the slope marker with positive 69.9 degree. Similarly, for all the isoclines, I have drawn the angle of the slope marker. And as you know, that the initial point should be given to you. In this case, I have taken the initial point as 1, 0. And you all already know, I had explained in my last class that how to find out the initial direction of trajectory. For this case, I have found that the initial direction is downward. So and since the initial point is 1, 0, so from that point you have to draw a line parallel to the slope marker on this isocline itself, and you also have to draw a line parallel to the slope marker on the next isocline. So from that point, for the next isocline, this is the next isocline for that point, and the for this isocline, the slope marker is this. So here I am drawing here a line which is parallel to this slope marker, and get a bisector, extend this bisector to the next isocline and repeat that process. And as you know, as you see that the trajectory is now moving in this direction. The trajectory is now moving in this direction. Now the graph paper is now fed. You can follow my sketch pen. So see, the trajectory is moving this direction. See, now this is not the circle, right? Because as I go further with the next isocline and the next isocline and so on, it will try to converge, right? But what will happen that ultimately where is it going to? My question is that if the initial point is this, then if I find out the initial direction and using the isocline, the trajectory is moving. But the trajectory is moving to where? The trajectory is moving where? Today, from this point, I will start my theory that where the trajectory is moving and why. See, this for this case, as I have taken the example of this differential equation, which is a case of underdamped system. However, it is also a linear differential equation, and the trajectory is not now circle, rather it is trying to converge towards origin. See, maybe before finally converging at the origin, it may circle the origin one or two or three times. It depends. Okay, now you can ask me that, sir, should I uh, for, should I do this process for indefinite times? No, it is not possible to draw the phase plane trajectory for all, because you don't know that how many encirclements of the origin may happen in this case. Because if you consider the time response concept, and this is since zeta equals to 0.5, which is an undamped system, and zeta, if you know that the value of zeta, when the value of zeta is close to 1, it becomes critically damped system. So when the value of zeta is close to 0, it is undamped system. Okay, so the oscillate for the zeta equals to 0, which is a case of oscillatory, and for the case where zeta equals to 1, which is a case of critically damped system, this oscillation depends on the value of zeta in the time response. You can imagine. I hope that you can imagine, right? So in the time response, uh, the, the many times oscillations occur. Here also, in the phase plane trajectory, the encirclement of the origin will occur. But it is not possible, and for all the for when the trajectory is moving for when it is passing to all isoclines, you have to get the bisector and then extend the trajectory to the next isocline and follow this process. But it is not possible for all the cases, because I don't know how many oscillation or in the phase plane how many encirclement of the origin will ultimately will occur in this example. Okay, so so I will suggest you start from your trajectory from the initial point, take some isoclines. Okay, in this case I have taken the isocline at the interval of 15 degree. You can also take the isocline at the interval of 0 degree, 30 degree, or 45 degree. My point is that if you consider uh, much closer isoclines, much closer straight line, I mean, then the more smoother the trajectory will be. So I will suggest in this case, start your trajectory from the initial point after finding out the initial direction. Then take 3 or 4 isoclines. If it is not circle, then stop there, and then you extend this phase plane trajectory by a dotted curve. Now you can ask me that, sir, how do I put the dotted curve after considering 3 or 4 isoclines? I mean, where the trajectory is going to? My question is that where the trajectory is going to? From this question, I'll start my next topic, where the trajectory is going to. Now remember one thing, and so far I have taken two examples, and both the examples are coming from linear differential equations, right? However, for the first case, which was x double dot plus x equals 0, the trajectory is totally circle. So it is going to the, it is if the trajectory starts from the initial point, it is coming back to the initial point once again, and it will repeat. Okay. Now for this case, since it is not an undamped system, it is an underdamped system. So the system is stable. You can validate your stability theory from time response chapter as well, because if you remember the last semester theory, that for undamped system we call this as a marginally stable system, and for a marginally stable system the poles are generally complex polar, which are lying in the imaginary axis itself. Okay, for the undamped system the poles are complex conjugate and they are lying on the imaginary axis itself. Now since it is marginally stable case, that's why the phase-moment trajectory is circle. But today the example I have taken for explanation is not the case for marginally stable system. It is an underdamped system, and underdamped system is always stable, so it will not oscillate, and so on the phase plane trajectory it will not make, the trajectory will not make a circle, it will try to converge. Now the question comes again and again, that then where the question is that then where the trajectory is going to, if it is converging, then converging to where on the phase plane. So from this question I am beginning my next topic, which is the concept of equilibrium point or singular point. Concept of equilibrium point. Now what is equilibrium point? Equilibrium point is the point where, this is the point, right? This is the point on the phase plane where there is no movement of the phase plane trajectory. That means the phase plane trajectory is stopped here, right? So I can say mathematically that at the equilibrium point on the phase plane, the change of x2 and the change of x1 is not there, right? So what I mean is that what do I mean is that at the equilibrium point there is no change of x2 and there is no change of x1, so dx2 is also 0 and dx1 is also 0, right? So the equilibrium point is the point where there is no change of x1 and there is no change of x2, so dx2 is 0 on the equilibrium point and dx1 is also 0 on the equilibrium point. So if you remember the slope of the trajectory, what is the slope of the trajectory? The slope of the trajectory I have assumed as m, which is change in y-axis, which is x2 dx2, and by change in x-axis, which is dx1. So in this case, for the equilibrium point of the phase plane, it is 0 by 0, which is undefined. So I can define my equilibrium point such that there is no change of x1, there is no change of x2. That means the trajectory is stopped here, because and also the slope of the trajectory is undetermined. So if this condition is satisfied at any point on the phase plane, that point is called equilibrium point. I am repeating this concept once again. Equilibrium point is the point on the phase plane where there is no movement of phase plane trajectory. That means the phase plane trajectory stopped at that point. Now stopping of the phase plane trajectory at that point means that there is no change of x1, there is no change of x2, because the trajectory was moving due to the change of x2 and change of x1, but at that point there is no change of x2 and no change of x1. So it's very small change of x2, that is dx2 is 0 at that point, equilibrium point, and dx1 is also 0. Now if I can remember the definition of phase slope of the phase plane trajectory, which is same, which is equals to dx2 by dx1 is equals to, for this case, 0 by 0, which is undetermined. So this is the condition I can say for the equilibrium point. If the slope of the trajectory is undetermined, then I can say this is the equilibrium point. Now you see that you can also ask me that, sir, for a differential equation given to you, how can I find out the equilibrium point? First of all, you find out by taking proper assumption for the state variable, find out the slope of the trajectory, m equals to dx2 by dx1, and then check that for which value of x1 and x2 the slope of the trajectory becomes undetermined. That point is the equilibrium point. Now coming back to the next previous example, let me take another sketch pen of different color, say the orange color. In this case, where is my slope of the trajectory? I have to find out the equilibrium point, right? I have to find out the equilibrium point. Now where is my slope of the trajectory? This is m, this is the slope of the trajectory. Now let me write this expression once again. M is equals to minus x2 minus x1 by x2. Can you find out? Now x1 is the state variable for the x-axis and x2 is the state variable of the y-axis. Now can you tell me that for which value of x1 and x2 the slope becomes undetermined? For which value of x1 and x2 the slope becomes undetermined? If you find out that point, that for a particular value of x1 and x2 the slope becomes undetermined, that point is the equilibrium point, no doubt about it. Okay, so from this example I can easily say, if I put x1 is equals to 0, if x1 is equals to 0 and x2 is equals to 0, then the slope of the trajectory becomes 0 by 0, which is undetermined. So for this example, for this differential equation, origin, that is 0 0, x1 0, x2 0 is the equilibrium point. That means for this example on the graph paper, origin itself is the equilibrium point. So equilibrium point is the point where there is no change of x1 and no change of x2. The trajectory is coming, converging, may rotate around the origin, but ultimately it is coming back to the origin to stop, to end, because at the origin it is found that origin itself, in this case the equilibrium point, and the equilibrium point there is no movement of trajectory. The trajectory is trying from the initial condition, the trajectory is trying to come back to the origin. The trajectory is trying to come back to its equilibrium point. So equilibrium point is the point where the trajectory will try to come back if the system is stable. Remember, the trajectory from any initial condition or anywhere on the phase plane, the trajectory will try to come back to the equilibrium point. Wherever the equilibrium point, in this case the origin itself is found to be equilibrium point, the trajectory will try to come back to its equilibrium point if the system is stable. And remember, this is the case of under-damped system, and under-damped system is stable system. You know this, if you find out the Routh array, or you can check the roots. The roots are found to be left hand are found to be in the left hand side of the S-plane. Okay, and if you know already that if the roots are lying in the left hand side of the S-plane, the system is stable. And since this is the system is stable and the origin is found to be equilibrium point in this case, so the trajectory will come back, will try to come back to its equilibrium point. But for the previous example, since this is the differential equation is coming from undamped system, and for the undamped system, the if you solve the roots of this differential equation, then you can find out the roots are lying on the imaginary axis itself and they are complex conjugate, and this is the marginal stable case. And for marginal stable case, and you can also find out the equilibrium point in this case. Where is the slope? Where is the slope? This is the slope, right?